General theory of relativity is known as human most successful theory in physics. But have to ask what is the reality actually behind it? To understand it, you need to study general relativity, but not as a student, but as a person who tries to understand the truth behind the possibly the greatest theory of all time. So we'll try to understand general relativity without making this boring math lecture, because general relativity is math heavy. Einstein field equation itself have 15 pages of matrix calculation. Theory might seem fun and math is as much abstract it can actually get. But if you are not a math person, you don't need to worry about it. You just need to understand the why behind it. Why do we even need this math? Well, this started from Einstein's happiest thought of his life. Well, that is someone falling from a building. Einstein found out that if we fall from a building, we are literally hovering in space. We don't feel the weight at all. The real reason we feel the weight, that is ground is pushing us upward, and or we are pushing ground down. Everything's relative. When we fall down from the sky, there is no ground. That when we fall down from the sky, there is no ground to weight us. It's just a free fall at 9.8 meter per second. If there is no air friction, it's like exactly hovering in space. Now either you falling to earth or earth coming to you, that matters relative what frame you are using. But what Einstein thought, this is that we follow a straight line always when we fall down. It might be a geodesic line in a curved surface. Now what is geodesic actually? Without math, you can take an analogy how plane flies around our world. It takes shortest path to reach the distance, but going to straight is not always the shortest path, because this map is 2D, but our real world is 3D. So actually, to move the shortest path or shortest geodesic path, we exactly need to move this path, not a straight line. This is the point of geodesic, where the geometry changes with dimension. So Einstein thought this math may be something that says a curved surface is a 4D coordinate and straight line in 3D real world, and the 4D coordinate system is space-time. Well, I talked about a space-time at this video, you can check it out. Anyways, a fascinating thought is as hard it is to apply. Einstein alone could not do the math. He needed a lot of physicists and mathematicians to do the math. Also, Bernhard Riemann, a German mathematician who invented Riemann geometry, introduced the concept of manifolds, matrix, famous, would not have existed. Ilwin Bruno Christoffel developed the foundational equation of differential geometry, including Christoffel's symbol, which tell you how coordinates changes across the space surface. They are essential for writing out covariant derivatives in GR. Ricci Curvature and Tullio Levi-Civita. These are two Italian mathematicians invented tensor calculus at that time called absolute differential calculus. Between 1887 and 19, they created the Ricci tensor and the mathematical rules for manipulating quantities that remains invariant regardless of the coordinate system. They built the exact toolkit that Einstein later adopted. More others like Hilbert, who works on Einstein-Hilbert action, Neother, who given conservation theory behind. This was not as easy theory to make, but most important question is what for? Space-time is not a real thing or fabric of reality. It is just useful coordination for math, and it bends by the mass using the stress energy tensor. That is, the Einstein field equation doesn't have mass. He used stress energy tensor as proxy of mass. Stress energy tensor, however, is not hard to understand. It's just a tensor of energy and momentum and stress, like strain and like shear and pressure. It just say that it's a physical part of the whole equation. That energy momentum is converted into a metric tensor that is known as the energy density, or energy at 1 cubic volume of space time. You can see I made a 2D simulation of the same thing. Mass that is created by energy momentum tensor, and that energy momentum is converted into this metric tensor. Its curvature can be transformed by the Christoffel symbol. But anyway, when their smaller mass comes, then they feel attracted, they fall down on the curvature, what we call attraction. Yeah, this is a simplified representation. Real math is 4D space-time math abstract, and the curvature is all calculated in 4D manifold, then used in 3D world. It looks beautiful indeed, but what use did it have actually? Well, different things like predicted the black hole by short-cell metric tensor. We found this equation, but well, the whole concept of black hole is gravitational field is that strong that even lights can't come out. Even though light doesn't have some mass, but escape velocity even is not about mass. Even in Newton, it was never about mass. Oh, you also, I talked about lensing on this video. You can check it out. It works just like lens that distorting vision, deflecting light from its original path. That's why the object looks displaced from where it is. And there is an angle between displacement that is called the gravitational deflection angle, which is just this equation. But you can find the same thing using Newton too. But instead of 4, it's 2. But what is the reason? Reason was told the time dilation uses another 4D, but the real reason is much weirder than it. Time dilation is not real, but the mathematical consequences of changing the coordinates and dimensions. Instead, Newton has 2 dimensions to work on. That's why it was 2, but GR works on 4D. That's why it became 4. That does not make Newton wrong, and that means GR works different frame, but to make the frame valid, they need to add consequences of time. The main problem is not what is wrong or is right, rather it is about philosophy. Neither of them are wrong or better than other, rather different philosophy of seeing the world. I used to think that we should maybe done with Newton, and still up to this day it works perfectly without any 4D space-time in it. Newton gravitation is complete by itself without need a better frameworks like GR. GR is useful, but also it has limitations of its own. It has some limitation that Newton has. The problem is singularity and action is distance. Assumption by both theories suffers from it. Gravity treat space is as gravity or treat space as a math of nothingness that can be carved on its own in 40 dimensions just to make the math work. But underlying structure of the whole field is still a mystery. It hardly can be called physics, and it does not say it is better than Newton. It does not say that it does anything more than what Newton does. It's up to you the what philosophy is better for you, time relative or absolute.